Hello dear students, so today we are going to see a hands-on on how to implement a simple linear regression neuron model. So what are we trying to do here is pick up a linear regression model of the mathematical equation y is equal to 1.477x plus 0.089 plus epsilon. So as I already discussed, you have the parameters of weights and biases, something assumed by yourself here, and also as discussed we are also taking into account observational error. So now we will try to implement this particular model using Python. So what are we going to do here is, first we will as usual import NumPy, because we are going to do a lot of mathematical calculations, and then we start with an empty list, and then we try to pick up a random sample from a uniform distribution of input samples. So what are we doing here is x is what we have taken as an input as a random uniform distribution, which is your Gaussian distribution over the range of -10 to 10, and then from there what are we going to have, apart from this, what are we going to have is the noise, that is your observational error. That is, you have here EPS, that is epsilon, as observational error, again normally distributed model for over the range of 0 to 0.01. So these two are randomly generated input and observational error, and you are going to pick one sample at a time for every time you calculate this particular model. The model output with random errors is what we are going to write is actually y is equal to 1.477x plus 0.089 plus epsilon. Alright. So this is your you initialize your program with, and what are we trying to do here is whatever data that you generate, you append it into our data list, and then you try to convert that into a two-dimensional NumPy array. I suppose this is very simple for you. Now what are we going to do here is, here I am writing overall my three methods. The first method that I am going to write here is about calculation of mean square error. So mean square error is dependent on weights and bias, right? And what are we doing here is we are passing the parameters as weights and bias and points. Alright, so total error initialized to 0, and then what are we going to do here is we are going to take the ith input and the ith output, and we are trying to calculate the total squared error. So as I already told you before, y is already present with you through your previous model that we have just given, and what are you trying to predict is out of the weights and biases. So mx plus c, that is wx plus b. Wx plus b as discussed is your predicted output, y is your actual output which is present with you. So the error between these two is the difference between these two, so which I have taken it as y minus, y is your actual output, predicted output is wx plus b. So difference between these two are going to give you the error between them, but we want MSC, so squaring this error and then trying to calculate the mean value when you do here, returning the total error divided by the number of length of the points. So when you just add up, you accumulate the sum overall all the samples of this error, you get the total, and the total divided by the number of points will give you the average value. So thus you have calculated in this method mean square error. Once you are done that, you are going for the step gradient. So firstly I initialized the gradients as 0 as usual, and then I calculated here using gradient formula. So what did I get over here? dl by db gradient of mean square error. I mean, when you differentiate this mean square error, you take this total error and you try to differentiate this particular value. Alright, so suppose I differentiate it with respect to b, so what am I going to get? B gradient. Alright, when you differentiate with respect to b. So what do you get here is, when you differentiate this particular equation, you get 2 into, you will get wx plus b minus y, and the other part will become 0. Now similarly you will calculate w gradient, that is again the total mean square error, you will try to differentiate it with w. Alright, so if suppose you are writing error as e, suppose, then dou E by dou B is going to give you B gradient, dou E by dou W is going to give you W gradient. So, here directly I have used this particular formula. Alright, and I try to calculate B gradient and W gradient out of it. Once I get that, I have to implement, I have to update this using gradient descent formula, which we have already discussed. So, new value of any parameter that you want to update is going to be old value minus eta, nabla and E. So, this we have already discussed. Whatever gradient you are calculating, that should be present. There should be a fixed learning rate. Then when you multiply these two, you will be subtracting it from the previous value. Thus, you will get your updated value of whatever parameter you want to update. So, here what I am going to do is, I am going to decide a learning rate and keep it as say LR. So, I am having learning rate here as LR in place of eta. I am writing here as LR into whatever gradient value that I get, and you have the updated value of bias as whatever is the current value of bias minus eta into the gradient of bias. Similarly, the same thing is repeated for the weights. So, now what you do is, after this particular method is incorporated, you get the updated value as per gradient descent. Once you have got all this, first you got MSE, then you have got gradient descent, and then you try to implement it now. So, what are you trying to do here is, you are writing initial values of B and W bias and the weight that you have already thought of, and then you start with iterations. You call your step gradient method that we have just written, and then you pass on with your initial values of bias and weight, and whatever data you have, along with it you will also fix some learning rate. Learning rate should always be very small, like around 0.01 or 0.1 also you can take, but not beyond that. We try to go, learning rate determines how fast you come to the minima. So, if you take learning rate quite high, then there are chances that you can skip the minima. So, you always try to keep learning rate slow, but not that slow also that it affects your model in terms of computation efficiency, but then you try to make it strategically a little low, but without affecting much to your model. So, now you are passing initial bias, initial weight, your data points and your learning rate to the previous method that we have written, so that you get updated value of your bias and weight, and for every updated value you would calculate the mean square error, right. So, now what I am doing here is, I am trying to print this iteration step and whatever loss that I am going to get, and the updated weight and the bias. So, once I get out of this particular function, I will get the final value of the weight and the bias. So, now I am writing my final function, the main function. So, what I am going to do here is, as discussed, like I am choosing this particular mathematical equation 1.477x plus 0.089 plus epsilon to determine the simple linear regression, and I chose my values of x and epsilon, randomly generated values. Now, once I get that, I initialized my learning rates, and that is 0.01. As discussed, it is very small. Now, initializing the weights and the bias, and I am fixing the number of iterations as 150, and then I am calling my main function of gradient descent, so that I get the updated value of my weight and bias with least going towards the direction of least error, mean square error, and then I calculate the loss, and then I print the final loss along with it, weight and bias. So, if I run this particular code, then what I get is, for iteration 0, you can see this was my loss of around 3.9, and these were the values of the weights and biases, that is 1.16 and 0.02 respectively. Now, as you see, I move on with the number of iterations. I am finding very much decrease in my loss, and thereby the difference in the weight also, you can see how the updations of the weight took place. So, as I started initially, B was around 0.02 and W was 1.16. At the end of 50th iteration, I got updated value of my weight with the decrease in the loss function. How do I update with the gradient descent algorithm with every iteration? At 50th iteration, I got 1.47, and then B is 0.06. Then similarly adjusting, updating as soon as we reach 150, because that's the maximum I kept. So at the 150th iteration I got almost a loss of 0.00, so almost a good accuracy that I am getting, and then I am having my weight as 1.477 and bias is 0.008. So this is the best pick of weight and bias that will give you the minimum value of loss function. So with this, what you have learnt, whatever value you can assume with weight and bias, but you have to pick up the best fit value so that it gives you the least mean square error. So when I applied my gradient descent algorithm and chose the formula of updated value is equal to whatever be the old value minus eta and gradient function whatever for weight or bias that I am choosing gradient. When I applied this particular formula and updated the parameter that I needed over several iterations, then I could say that till the point where I get the minimum value, that is here that what I am expecting is nearly 0. So till the point will I find the minimum value of my mean square error, that particular point are the best fit point in order to get the least amount of error in the actual value and the predicted value. So this was a gist of how you could implement a gradient descent algorithm. I would like you to pick up several other models under simple linear regression and then do some task over it so that you get a more hands-on experience over how to implement a regression neuron model. That's it for today.